So let me share the screen from where we left so that I can immediately begin the lecture. Now, this is where I stopped at, students. Now, in the past, we have written the Lewis dot structures for simple atoms. Now we want to move ahead and see whether we can do the electron dot structures Lewis for some compounds. And when we talk about compounds here, we are talking about polyatomic ions. And how do we do that? The first thing is to calculate the total number of valency electrons. The total number of valency electrons here, we are talking about the valency electrons for all the atoms that are involved in that particular compound. So calculate the number of valency electrons. And number two, write the skeleton structure of the molecule or ion. And number three, distribute electrons to the atoms surrounding the central atom. The central atom in this particular case is the less electronegative atom in that particular compound. So that all the atoms are going to satisfy what we call the octet rule. Then if there are any electrons remaining, then we are going to associate them with the central atom. And I'm going to illustrate this one using some examples. And the first example that you can see is what we have here. Now, if you look at this, we have sulfur and we have 2 atoms of chlorine. So the first thing as illustrated in the slide that follows is to determine the total number of valency electrons. Let me maybe carry this particular compound here so that we can explain how this is being done. So if I can paste it here. I want to paste it somewhere. So when we look at determining the total number of valency electrons, when you write the electronic configuration for sulfur, what do you find? Where do we find sulfur in the periodic table? And what are the values? Somebody wants to talk?
It's in group 6.
It is in group 6, eh?
Yeah.
That means we have 6 valency electrons, isn't it?
Yeah.
So then you can see this is the 6 valency electrons. For chlorine is actually again in group 7. So it has 7 valency electrons. So how do we calculate the total number of valency electrons? In this particular compound here, we have 1 atom of sulfur, and that atom of sulfur has 6 valency electrons. Now there are 2 atoms of chlorine, which is found here, and each of them has 7 valency electrons. So you realize that this one is 6, and this one is 14, and when you add the 2, we are going to get 20 electrons, which we can also describe them as 10 pairs of electrons. Now, what are we supposed to do now? We come up with a sketch. And this sketch here, we are only interested in ensuring that the outer atoms have the octet structure. What are these ones we are calling the outer atoms? The outer atoms are all other atoms apart from the central atom. The central atom we are saying is the one that has a lower electronegativity. So if you see what we are doing here, we are looking at chlorine and the chlorine here, and we have distributed these electrons so that chlorine has 8 electrons surrounding it, and the other chlorine has 8 electrons surrounding it. In the process, you realize that there is a pair of electrons shared here between chlorine and sulfur, and another pair of electrons here shared between chlorine and sulfur. And that shared pair of electrons can actually be represented here on this other side as a single bond, the way you can see. Now, how many electrons are we looking at? We are looking at 20 electrons. So the question is, in this distribution, how many electrons have we used? We have, you can count these dots. These dots are actually going to give you the number of electrons that we have already used. So you can see there is one. Let me pick my pen again. There is one pair, another pair, third pair, fourth pair, fifth pair, sixth pair, seventh pair, and eighth pair. What are we saying here? We have already used 8 pairs of electrons to already form what we have here. And how many electrons did we have? We had 20 electrons. So when we have used 8 pairs, it's like using 16 of them. So when we take 20 minus 16, you realize that we have 4 electrons that we have not used. The electrons that we have not used now are going to be distributed in the central atom. And that is why we have these 2 electrons here and another 2 electrons here. And when we do that, you'll realize that we will have distributed all the 20 valency electrons. Therefore, this is what we have, or you can also represent it like this, and also represent it like what you can see here. I'm going to give another example. If you have not understood this, I'm going to give another example. So the other example is actually in the slide that follows. So if you look at this slide, you have this particular compound here. And if you look at this particular compound here, the question now is, how do we write the dot formula, the Lewis dot formula of this particular compound here? So that is what I want us to discuss. This is what we call the chloryl fluoride. So in chloryl fluoride now, it is not chloryl fluoride, sorry. It is chloryl carbonate. So what we are going to do here is we look at carbon. Now carbon, if you look at that electronic configuration you did in is 2, 4. So the valency electrons are 4. This is what we have here. The valency electrons for oxygen are 6. The valency electrons for chlorine, we have looked at it. They are 7. Now, then we look at the total number of valency electrons. If you look at the total number of valency electrons, then what are we supposed to do? Then we look at, we have carbon giving us 4 electrons. We have oxygen giving us 6 electrons. Those are 10. And then we have 2 chlorine atoms, and each of them is giving us 7. So that is already 14. So when you take 14 plus 10, that's how you are getting these 24. These 24 here. So the next thing, we now start distributing. And how do we distribute? We look at what we have here. We are going to look at all, when you look at all these atoms, you will realize that it is carbon, which has the lowest electronegativity. And therefore, we are going to ensure that oxygen is okay, and the other 2 chlorines are okay in terms of distributing these particular electrons so that we can get an octet rule. And that is why you have this chlorine here is surrounded by 8 electrons, if you count them. Similarly, this chlorine here is surrounded by 8 electrons, again, if you count them. And this oxygen here is surrounded by 8 electrons, if you count them. So we have ensured that the outer atoms are already having a full octet. Therefore, in the process, we ask ourselves, how many electrons have we spent so far? So when you have this structure here, when you have this structure here, you can just look at those electrons that are shared, like these ones. Those are electrons shared. Those are electrons shared. And those are electrons shared. On this side, they are the ones represented by this single bond here, this single bond here, and this single bond here. So that is what we have. So the question is, after we have ensured that the chlorine atoms and the oxygen atoms have the 8 electrons that they require, the octet. So we ask ourselves, what is the total number of electrons that we have so far used? So we have a pair, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pairs. Now, 12 pairs constitutes a total of 24 electrons. So how many valence electrons do we have? We had 24. We had 24. You can see from here, we had 24. But we have already used all of them. Now, in the process, you will realize that this carbon here, we have used all the electrons that were available, but the carbon here is only surrounded by 6 electrons. And the 6 electrons that are surrounding carbon, you can see that we have this one, and this one. So we need to ensure that it is experiencing 6. That is where we are saying that since there are not enough electrons to give an octet, especially for carbon, then we actually borrow electrons from one of the atoms, because you can see these other atoms have lone pairs of electrons. And therefore you can see we have borrowed this pair of electrons, and we have brought it here so that another bond is formed, but this bond is formed in such that the bonding electrons are principally coming from oxygen, so that we end up forming this bond here. And then the other 2 electrons, the other pairs of electrons, this one and this one, are remaining as lone pairs of electrons. Now, once we do that, ladies and gentlemen, you'll realize that all the atoms that we have in this particular compound have the octet configuration, and we have satisfied the rule that is required. So that is how this particular compound is going to look like. If we move on, then we do have an exercise here, and the exercise requires you to write the electron dot formula of iodine, nitrogen trifluoride, carbonyl fluoride, because the other one was a carbonyl chloride. We also have tetrafluoromethane, which is also known as tetrafluoride or carbon tetrafluoride, sorry. Then we have nitrous acid. Then we have HCN, which is hydrogen cyanide. It is sometimes referred to as a prussic acid. Then we have BF4 negative, which is tetrafluoroborate. And then we have PH3, which is phosphine. So if you follow the example that we have done, you will be able to come up with the Lewis dot formula for these particular compounds. Now, let me talk about the delocalization of bonding electrons. When you talk about delocalized bonding, here we are talking about a type of bonding in which the bonding pair of electrons is not associated with particular atoms, but it is associated with a number of atoms. And for example, I'm going to look at this compound here. Let me see whether I can bring this compound here. Are you able to see this compound here, students?
Yes.
Now,
Yes.
Yes.
this is a benzene ring. Now, this benzene ring is such that this is a carbon, this is a carbon, this is a carbon, a carbon, a carbon, and a carbon. Now, you also realize that the double bond is between this carbon. We have a double bond here. We have a double bond here. And we have a double bond there. Now, the question is, why can't we have it such that, let me see whether I'm going to have another one. If I draw this one here, but this time I want to rotate it. It rotated properly. Yes. No, it's not the way I wanted. Just a moment. No. No, just a moment. I want to make it better the way I want it to look like. Now, look at what we have there. So you can see in this structure that I have here, I have now changed the positions of the double bonds so that we have this carbon here and this carbon here. This is where we had a double bond in this, but here we do not have a double bond. In other words, I have swapped the positions of the double bonds so that now this, we have it here, here, and there. Can you see that? Now the question is, are these two compounds different? No, they are not different. These two compounds are actually talking about the same benzene. Now, what does it therefore mean? If you have a double bond that can occur in these carbon atoms and also in these carbon atoms, then it means that this particular compound can be represented in both ways. And we actually use what we call a double arrow like this to show that both of these two possible structures mean the same thing. And this is what we call a resonance structure. For purposes of benzene, we actually represent, I want to do away with these things. We usually represent these resonance structures by drawing something like this. In some cases, you'll be able to see a structure looking like this. That stands for all the resonance structures that we have. So whenever it is possible to actually write two different structures, then we usually write all the possible structures and then use an arrow to mean that you can either write it this way or the other way. And we call these structures resonance structures. And that is explained here. A single electron dot diagram cannot properly describe such a structure that can have two different ways of doing it. But again, you realize that when you are doing that, the total number of atoms and the charges are not different. So we use the resonance description so that the electron structure of a molecule or ion having delocalized bonding is given by writing all the possible formulas. And I have illustrated this using the benzene. And we connect the possible formulas using a double-headed arrow. And we are going to illustrate that using some examples here. And one of the examples is what we call the carbonate ion. Now, the carbonate ion has a structure the way you can see here. So one possible Lewis dot formula for this carbonate ion is this one here. So if you look at this carbonate ion now, the question is, if you look at this, you'll realize that Oh, I think I have distorted it. Let me just bring it back to where it was. So you'll realize that there is a central atom, which is carbon, and it is surrounded by some oxygen atoms. Now, these oxygen atoms are such that one of the oxygen atom has a double bond, and the one that has a double bond has two lone pairs of electrons, while the other two oxygen atoms have three pairs of three lone pairs, and they are attached to the carbon through a single bond. So the question that somebody would ask is, why do we only choose this oxygen here to be the one with two pairs of lone electrons and a double bond? Why can't it be this one or this one? And that is why you can see down here, the first structure is what we have above here. In the second structure here, we have moved this characteristic of two pairs of electrons to this particular carbon here, and also shifted the double bond. While in the third one, this is not supposed to be like this. I will correct this. This is supposed to be on this particular carbon atom. I mean, on this particular oxygen atom. Because if you look at this and the first one, they look the same. So in this last one here, the double bond is supposed to be in this third oxygen atom. That means that when you draw that way, it is going to give us three possible structures. And those three possible structures are talking about the same thing, which is the carbonate ion. And you can see in between, we are using double-headed arrows to stand for that. Another compound that we can use is what we call the acetate ion. Now, the acetate ion is drawn like this. This comes from acetic acid or ethanoic acid. Therefore, you cannot call it the ethanoate ion or the acetate ion. How do we draw this particular ion? You can start these processes by looking at the total number of valence electrons, because it comes from what we had just discussed above, looking at the total number of valence electrons. And then you distribute these electrons using the carbons as the central atoms. And once you do that, that is explained in this slide. So you can see the valence electrons, there are two carbon atoms, and each of the carbon atom has 4 valence electrons. There are 3 hydrogen atoms, and each of them has 1 valence electron. There are 2 oxygen atoms, and each of them has 6 valence electrons. You can see there is +1 here. The question is, where is this one coming from? This compound here is negatively charged. This negative charge is as a result of an extra electron, which is the electron we are putting here. So if you look at that, you realize that the total number of valence electrons here are 24. And therefore, you can distribute them and you are going to get 2 possible structures as they are given here. So for those 2 possible structures, then we put a double-headed arrow in between so that we can talk about a resonant structure. So having said that, maybe we can talk about an exercise here. It's an exercise that students, you can try. We have nitric acid here, we have sulfur trioxide, we have a nitrite, and we have a nitrate. You can use the same and see whether you can come up with different resonance structures for this particular compound. Now, I am going to revisit something that I said in the morning, that some molecules have electron dot structures that satisfy the octet rule. Some they have more electrons than the octet rule, while others have less electrons than the octet. So how do we justify that? I'm going to give you a number of compounds such that some particular atoms in that particular compound will not be having the 8 electrons that they require. And some examples are here. For example, look at beryllium difluoride. Beryllium, if you go to the periodic table, you know beryllium has only 2 valency electrons. So this is a covalent bonding whereby an atom from fluorine and another atom from beryllium form a single covalent bond here. Another atom from fluorine here and an atom from beryllium form another single bond here. So you'll realize that for the fluorine, the 2 fluorine atoms here have the 8 electrons that they require. But beryllium is only going to have 4 electrons. That means that this beryllium here has less electrons than the octet. The other one that you can see is the boron trifluoride here. Again, you know the electronic configuration of boron. Now you'll realize that this fluoride here has 8, the fluorine here has 8, the fluorine here has 8, but this boron here is only surrounded by a total of 6 electrons, which means that it has less than what it requires. So that is another example of a particular atom which has less electrons than it requires. Now, if you look at the other compound here, which is aluminum trifluoride, this is not the ionic compound. Remember, we said that this group of compounds can have cationic character and anionic character. So it has covalent, it can have ionic compounds and covalent compounds. So what I'm showing here is aluminum actually having a covalent character. And you know, the valency electrons here, you'll find that there are 3 valency electrons because of 3s1, 3s2, and 3p1. So those 3 electrons are actually involved in the formation of bonds, covalent bonds with fluorine here, so that each of the fluorine atoms has an octet configuration, but the aluminum here is only going to have 6 electrons. So these are examples of some atoms in compounds where too few electrons are going to be found, but actually fewer than the 8 that are expected. Now, we may have very many more examples, and in a short while, I'll be showing you some atoms that have more than the 8, which is required as we discussed. So there are many more examples of central atoms with more than octets, which I'm saying I'm going to give. Now, because elements of the 3rd period and beyond have a d subshell, where does this one come from? When you look at sulfur, if you look at sulfur, you'll realize that sulfur is atomic number 16, and therefore you are going to write 1s2, 2s2, blah, 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 blah. And then you are going to have a 3p something. Now, this 3p4 here that we are going to have, it means that this statement shows, you can see we are saying that they have a d subshell. The moment you talk about n is equal to 3, n is equal to 3 will have s orbitals, will have p orbitals, will also have d orbitals. Now, the only difference for phosphorus, chlorine, and sulfur is that these d orbitals are not going to have any electrons. They are not going to have it. They are empty, simply because for sulfur, you are writing 1s2, 2s2, 2p6, 3s2, 3p4. That's what we have. Okay. Remember, these 4 orbitals in the 3rd energy level is not already filled. It has a 3d also, but this 3d is empty because we do not have sufficient electrons to fill in these 3d orbitals. So the same thing applies to the phosphorus and chlorine. And that is why we are saying, that they can expand their valency electrons to accommodate these d orbitals. But when you talk about the elements in the second period, that is n is equal to 2. You know, n is equal to 2, we can only have an s orbital and a d orbital. We cannot have a d orbital for n is equal to 2 because they are not available actually. Now, if you look at this compound that I'm showing you here, students, this is a phosphorus pentachloride. Pentachloride, not fluoride. Phosphorus pentachloride. We just make a simple correction here. So what is happening?
Excuse me, sir.
Yes, there are two hands that are raised.
Okay, I just had to tell you that I'm with Denver on the same computer. He
Yes.
had an issue with his laptop.
So please remind me when I'll be taking the attendance.
Attendance. Okay, I will.
Please, thank you for that.
Okay.
There's another student whose hand is up.
Yeah, it's mine. I just wanted to tell you we're a little fast this afternoon. Maybe you could pardon from slide 86.
From slide 86.
Yeah.
Okay. Slide 86. Let me go there very quickly. Here we are showing some central atoms that are deficient of electrons, that have less electrons than the 8 that are required. And we have given, for example, beryllium in this kind of a compound. You realize that there are 2 electrons in this bond, and there are another 2 electrons in this bond. So whereas there are 8 electrons surrounding the fluorine atoms, the beryllium is only going to have a total of 4 electrons, 2 here and 2 here. So this is a case of a compound whereby the central atom is going to be having less than the 8 electrons. The same thing applies to a boron here, because now this boron is going to have 2 electrons here, 2 electrons here, and 2 electrons here. And the total electrons here is going to be 6, whereas it requires 8. Same thing applies to aluminum here. And this is a covalent bond. It's not an ionic compound. So whereby you have 2 electrons, 2 electrons, and 2 electrons. So the total number of electrons that you have here will be 6. So these are examples of electron deficient central atoms. I said that we also have others that have more than 8 electrons in their central atoms. And the first one that I was going to show is the phosphorus pentachloride here. Now, this phosphorus pentachloride, you'll realize that the phosphorus here is surrounded by 5 bonds, and you know each bond carries 2 electrons. So if you take each of these bonds, 5 bonds multiplied by 2, you realize that this phosphorus here is experiencing a total of 10 electrons. So it is in excess by 2. Again, if you look at this compound here, which is explained here, we are still using the total number of valence electrons. You'll realize that one, this compound, we have a fluorine, a fluorine, a fluorine, a fluorine, and a fluorine. So there are 5 fluorine atoms. So that one is actually giving us what? It is giving us a total of 10 electrons. Now, what is the total number of valence electrons that we have here? This compound has 5 fluorine atoms, and each of them has 7 electrons. So this alone gives us 35. Then the iodine alone, which is also a halogen, has 7 valence electrons. So the total is 42. So when we begin distributing them, what is going to happen? We are going to realize that forget that these two electrons that you can see here. Let us distribute first. You have this bond, this bond, this bond, that bond, and that bond. Those are 5 bonds, and they carry a total of 10 electrons. Then these fluorines here each has 6 electrons, and because there are 5 of them, you'll realize that they are 30. So 30 plus the 10 will give you 40, but the total is 42. So the question is, where do we take the remaining 2 electrons? Those remaining 2 electrons are actually put where I am pointing here, so that effectively you'll realize that this iodine has a total of 12 electrons surrounding it. So again, is an example where the number of electrons surrounding the central atom is more than the required 8. We continue. This is a xenon tetrafluoride. So you'll again go through the same process. You calculate the total number of valence electrons, and when you do a distribution, it brings you something like this. So the total number of valence electrons are 36. And where does this 36 come from? Xenon is a noble gas, so it has 8 electrons. Then this is not oxygen. These are supposed to be fluorine. I'll correct this. It's supposed to be fluorine. Each is 7. So you multiply by 4 of them, you get 28. So 28 plus 8, you get 36. So here we are supposed to ensure that the 36 electrons are sufficiently distributed. So let us see what happens. This fluoride here has 6 electrons. This one has 6. This one has 6. This one has 6. So if you look at the 6 multiplied by 4, you are going to get 24. Then these bonds here are going to have 8 of them. So 24 plus 8 will give you 32. But remember, we are supposed to account for 36. So the question is, where are we going to take the remaining 4 electrons? Those 4 electrons are here. Those 4 electrons are here on both sides of xenon. And then you realize that the total number of electrons in xenon now are no longer 8, but now they are 12. Now, let me move to something different, students. I will stop at around 4:30 to take a few questions, and I also take the attendance. So let us look at something we call the formal charge. Now, when we are looking at the formal charge, there is a hypothetical assumption that we make, and we are saying that the formal charge on an atom is the Lewis formula. In the Lewis formula is a hypothetical charge that you're going to obtain when you assume that the bonding electrons are equally shared between the bonded atoms, in the sense that they are shared in the middle. Not whereby we are saying some electrons are going to be closer to one atom than they are to the other. And number 2, that the electrons of the lone pair, they belong to only one atom. You can only associate them with one atom. And I'm going to give you specific formula and examples on how this one can be calculated. What are the rules for calculating the formal charge? The formal charge, you look at half of the electrons of a bond are supposed to be assigned to each atom, because we are saying that the electrons are contributed and shared equally. And number 2, the electrons in a lone pair are assigned to the atom to which that particular lone pair appears. I am going to explain this with particular examples if you pay attention. So here we are. How do we get the formal charge on the atom? The formal charge is equal to the total valence electrons of the particular atom that we are looking at minus a half the number of electrons in a bond. A half the number of electrons in a bond, you are simply talking about the number of bonds that appear minus the number of lone pair electrons. I will again go ahead and give specific examples. Now, formal charges will actually have some advantages. So whenever you can write several Lewis formula of a molecule, you only choose the one having the lowest magnitudes of the formal charges. And when two proposed Lewis formulas or two possible Lewis formulas have the same magnitudes of formal charges, then you choose the one having the negative formal charge on the more electronegative atom. And number 3.
Sir,
Yes,
do you mind repeating number 1?
I repeat number 1.
Yeah, what do they mean by one? Choose the one having the lowest magnitudes of formal charges. That you mean like using the formula, like in the previous slide?
Using the formula, and I'm going to illustrate in the next slide using a particular example.
Okay,
Yes.
thank you.
So can I continue then? So
Yeah, sure. Just when we're doing the equation, do you mind just explaining that first
I
point
will.
when we're doing?
I will.
Okay,
I will. So when possible, choose Lewis formula that do not have like charges on adjacent atoms. And we are going to illustrate that using the carbon dioxide. So look at carbon dioxide. You know, these are two possible structures of carbon dioxide, because if you look at them, you'll realize that all the atoms have the maximum number of electrons that they need to experience in their outermost energy level. So the question is, can we calculate the formal charge for each of these atoms here? And we calculate the formal charge for each of these atoms here. So look, let us start with this. For each of the carbon here, we take, you know, the formal charge, you take the total number of valence electrons minus a half the total number of bonded minus the lone pairs of electrons. So if we look at the carbon here, for example, carbon has 4 valence electrons. Then we subtract a half the number of bonded electrons. When we are subtracting a half the number of bonded electrons, it's the same as counting how many bonds are here. 1, 2, 3, 4. Because this carbon here has 4 bonds. So it's just like counting the number of bonds that are attached to that particular atom. So they are 4. And why am I saying so? Because if you look at the total number of electrons in these 4 bonds, they are 8. And remember, we are taking a half of the total number of electrons. A half of 8 is equal to 4. So instead of taking that a half, just count the number of bonds associated with that particular atom. So they are 4. So does carbon have any lone pairs of electrons? No. So that gives you a 0. Now, number 2, the behavior of this oxygen here and this oxygen here are exactly the same in terms of structure. Therefore, we can only look at one of them because the other one is going to be a mirror of the first one. Therefore, what is the total number of valence electrons in oxygen? There are 6. How many bonds are there? This oxygen here has 2 bonds, 1, 2. We don't need to count this because we are only looking at one atom of oxygen. So this atom of oxygen has only 2 bonds. So we subtract 2, and we also subtract the total number of lone pairs of electrons. So it has 4 lone electrons. So we subtract 4, and the answer is 4. So if you look at the formal charge in this compound for each of the atoms.
Excuse me, sir. The number of lone.
The number of lone electrons.
Okay, thank you.
You can say there are 2 pairs. Okay? There are 2 lone pairs. So 2 lone pairs are giving us a total of 4 electrons. That is why we are subtracting 4. Is it clear?
Yes, yes.
So you will see that here we are getting 0, 0. Now, let us look at what is happening here. We start with the carbon. Carbon has 4 valence electrons. This carbon has 4 bonds. 1, 2, 3, 4. So we subtract 4. Does it have any lone electrons? No. We subtract 0, we get a 0. Now, the 2 oxygens are not the same, so we evaluate each alone. So let us start with this. This oxygen here has 6 valence electrons. How many bonds does it have? It has 1 bond. How many lone electrons does it have? It has 6 of them. So that gives us -1. This oxygen on this side has 6 valence electrons. How many bonds? The bonds are 3. How many lone electrons? They are 2. So that gives us what? It gives us a +1. So let us come back here. Whenever you can write several Lewis formulas, choose the one having the lowest magnitudes of formal charges. If you look at these structures, the formal charges here are 0, 0. Here we have a mixture of 0, -1, and 1. So the one with lowest magnitudes of formal charges is this particular option, and therefore this is the better, or this is the approved, or this is the stable configuration of the carbon dioxide. After all, when you are writing carbon dioxide, you've never written this, you only write this, okay? But chemically, these two are okay, only that when you evaluate further in terms of their formal charges, you realize that this one is going to be a more stable kind of a configuration. Other examples, we have sulfuric acid, for example, here. So this sulfuric acid is such that this hydrogen here and this hydrogen here are the same. So we can evaluate them similarly. This oxygen here and this oxygen here can also be evaluated similarly, while this oxygen here and the oxygen here can also be evaluated similarly. Then we look at what is happening here.
Sir?
Yes.
Can you please go back to the rules? I just have one more question.
Yes, we go back to the rules.
Yeah.
Here we are.
Can you just explain with the example what they mean by when 2 proposed Lewis formulas have the same magnitudes of formal changes, choose the one having the negative formal charge on the most electronegative atom? Are they just talking about the one for, like, you rather just choose 0?
Come again.
Can you just explain the second rule in relation to the example, just so
Yes.
like for visualization purposes?
Okay. Now
Thank
look,
you.
for example, look at this one here. Look at this one here. You see, the carbon has a 0. One oxygen has a -1. The other one has a +1. So what this rule says is that it talks about those charged particles, for example, a carbonate, for example, an acetate, those are charged particles. So we are saying that when 2 proposed Lewis formulas have the same magnitude of formal charges, choose the one having the negative formal charge on the more electronegative atom. So when we look at this example here, forget about this. Just forget about this. But assuming that this one was, for example, a chlorine, just giving an example, and this one was an oxygen. And then this chlorine is such that, let me go back. Then it is such that this one is -1, and this one is +1. Just another illustration. Then what would happen here is this. And then we have another configuration looking like this, whereby the charges are similar. Then when you compare the electronegativity of chlorine and that of oxygen, the electronegativity of oxygen is higher. I think this is around 3.6 or 4, something like that. And this is a 3.16 or something like that. Now, this one, if this one has a negative charge somewhere, and a negative charge, you find it either in a carbonate or in an acetate, then you would prefer to leave it with the one, we are simply saying that the negative form or charge on the more electronegative atom. Negative form or charge on the more electronegative atom. I think that is what it would mean. Let me see as we continue whether we have any of the examples that has an ion and see whether I can explain it better. Is that okay?
Yeah, sure. I don't get it, but if you can explain like with another example, sure.
I'm going
Okay.
to check whether we have an example as we continue. Then I'm going to explain. In the meantime, I was looking at sulfuric acid, and you can see that this hydrogen and this hydrogen are the same. This oxygen and this oxygen are the same, while this oxygen and this oxygen are the same. So you can calculate the formal charges of each of these and see. So when you look at these, here, what is the total number of valence electrons for hydrogen? Yes, students? Hello?
I think it doesn't have valence electrons.
Hydrogen has only one electron, isn't it? So the total number of valence electrons for hydrogen is 1. Then
Yeah.
we subtract 1 electron here because of one bond.
Yes.
Does it have any lone electrons? It doesn't have. So on that
Yes.
basis, this becomes a 0. So these are 0. The same here, these are 0. Now, this oxygen here and this oxygen here are the same. So what do we say? The total number of valence electrons here are 6. All right?
Yeah.
Then we subtract 2 electrons because of this bond and this bond.
Yeah,
Get 4, and we subtract the lone electrons, which are 4. We get what? 0.
0.
So we again look at this oxygen, which is the same as this. Here, the total number of valence electrons are 6 again. So we subtract an electron here, and we subtract 6. So we are going to get -1, which is actually explained here. So the oxygen atom gets 2 electrons from the single. I think we have explained. So one of them is going to have a 0. The other one is going to have a -1. This hydrogen here has a 0, while this sulfur here is going to have a +2. Now, so when we are writing them, you can see the way we are doing. The hydrogens here are the formal charge of 0. This hydrogen and this hydrogen. This oxygen here and this oxygen here are the formal charge of 0. But this sulfur here are the formal charge of +2, while this oxygen here are the formal charge of -1. So what happens in such a case, we balance these charges by having another bond here. So when you have another bond here, you realize that the formal charges are actually going to be becoming 0. When you recalculate, you realize that they are going to be 0. Let me see whether there is anything I have lacked. I seem to have lacked an ion, but let me see as we continue. These are further exercises. Now, let us look at this. For each of the following, use the formal charges to choose. So allow us to look at these these compounds at the end. At the end, which is it the bromate ion? Which one is that? Yeah, the bromate ion. Allow us to look at this at the end after I have discussed a few things. So before I go to the bond length, Can I take the attendance? Hello?
First way.
Can I take the attendance?
What if we finish first the class and we take the time?
You want us to finish first, eh?
Yeah.
No,
I think
it's
there's some
okay. Okay, I think we should take the attendance so that we can have a bit of time to like digest what's going on. I don't know.
So I take the attendance first, eh?
That's what I think.
There seem to be some background noise, eh? So let me take your attendance. Just a moment. I load the courses. As usual, I want to begin with Y. Actually, there's no reason as to why I start with Y. Okay. So we go. So Mustaf Abdinor.
Yes. Present.
This is so surprising. Eh? I don't know how this attendance is going to look like because according to this lecture, I've already taken the attendance. Eh? I think my colleague opened exactly the same because the attendance is already taken for today and posted. Eh? So I don't know how I can go about this. It's not something I can handle. For both classes, it is picking the attendance for the morning lesson. So let me continue, students, please.
Yeah, it's okay. We have all attended.
I like that. But you can see we are 43. I think in the morning we are 45. Eh? So,
Sir, I told you that I'm in the same class with Denver.
oh yes, yes, yes.
Yeah.
So we're 44.
Okay. So that was Anastasia, isn't it?
No, I have a question.
Yes, you have a question.
Yeah, Anastasia, I'm asking, would you please repeat slide 102?
1 or 2.
Yeah, and
Actually,
explain number
101.
C.
It is an exercise.
Okay, I was asking if you could like do one of them.
We try to do this, eh?
Yeah.
Okay. Let us go together and remember by 10 minutes past 5, we are supposed to be done, isn't it?
Yes.
Now, look, the question is, what is the total number? Yes, Lillian?
Okay, I really didn't understand whatever was going on with the sulfuric acid.
You didn't understand?
Yeah.
So can I go back there?
Yes, please.
Okay. This is sulfuric acid. We can try to calculate the formal charges. And let me use this color. That hydrogen and that hydrogen are the same, meaning that when we determine the formal charge of one, it will be equal to the formal charge of the other. Similarly, that oxygen and that oxygen are the same, meaning that when we determine the formal charge of one, it will be equal to the other. And this oxygen here and that oxygen here are the same, meaning that if we determine the formal charge, then they are going to be the same. Sulfur is only one. So how do we go about it? So look, you know, hydrogen is 1s1. So it has only one valence electron. So the total number of valence electrons here is 1 minus, how many bonds are there? Only one bond. Let me see whether I can move it up. Only one bond. Does this hydrogen have any lone electrons?
No.
No, it doesn't have, so you subtract a 0. And the answer that you get there is a 0. So this hydrogen and this hydrogen are the same. So we now look at this oxygen here. Let me see whether I can mark some of them. So you have done that. We have done that. So let us look at this. Let us look at that. Now you will realize that just one moment. I highlight what we are looking at. So we have looked at that. We have looked at that. So what we want to do now is that oxygen, which is going to be the same as this. And how do we go about that? We say that the valence electron for oxygen are 6. Because we're only looking at one of these oxygens circled in blue. They are 6. Then we ask ourselves, now, how many bonds are there in each of these? There are 2. So we subtract 2. Do they have lone electrons? Yes.
Yes.
How many electrons are there? Yes.
4.
They are 4.
4.
So we subtract 4. And the answer is going to be what? 0.
0.
So once we do that, we will have handled that and that. So next, let us look at this oxygen, which is also the same as this oxygen here. And what we do, we come here. Again, it has 6 valence electrons. How many bonds?
1.
We subtract 1. How many lone electrons?
6.
We have 6 of them.
Yeah.
And the answer here is
Minus 1.
-1. You look at sulfur. What is the number of electrons in sulfur? The valence electrons in sulfur?
I think 5. I'm not sure. I'm sure it's group 5.
Are you sure it is group 5?
No,
4.
I guess 4. Group 4.
Huh?
6.
6.
This is a group 6 element.
Yeah.
Remember, it is in the same a group with oxygen. Okay?
Yeah, yeah.
So for sulfur, we come here and say it has 6. I think I'm blocking something here. It has 6. We subtract. How many bonds does it have?
4.
4. Does it have any lone electrons?
No.
No.
0. So what is the answer?
2.
2.
Plus 2. So having said that, you realize that this one, no, sorry, should not have done that. You realize that this oxygen here is 0. I mean, this hydrogen here is 0. This hydrogen here is 0. This oxygen here is 0. The oxygen here is 0. Now, this one, if I may pick this, this is -1 and this is +2. That is +2. Now, a rearrangement of these electrons is going to occur such that One of these pairs here will come here and form a bond. One of this one here will come here and form a bond. Let us see what happens in such a case. You'll realize that in this particular case, sulfur will be 0. How is it going to be 0 now? Look, it has 6 valence electrons, then minus, what is the total number of bonds?
6.
6. Does it have any lone pairs?
No.
No.
So we subtract what? A 0. And what we're getting is what? 0. Can you see we have made it to have a lower form of charge than it had in terms of magnitude?
Yes.
Now, let us look at the oxygen. Remember, for oxygen, one of the electrons, these electrons here have been used. And these electrons here have been used. So let me clear. These electrons have been used. And these electrons have been used. They are no longer there. But there is a double bond here. And there is a double bond here. So let us see what happens. We calculate the formal charge. You realize that the valence electrons are 6. Okay? How many bonds are there? Just look at only one of these oxygen atoms. Only one of them. Yes?
2 bonds.
There are 2 bonds, so we subtract 2. How many lone electrons are there?
4.
You
4.
subtract 4. What are you getting?
0.
0. Can you see we have made that particular compound behave? Because when it has the lowest form of charge, then that is the structure we go for. That is the structure we go for. Is that okay?
No.
Excuse me.
Why are you saying no? Remember what we did for carbon dioxide.
It's not okay because I'm trying to wonder, like, in at first, oxygen had 6 lone pairs of electrons. So,
Yes.
did it contribute all the 2 for the in this bond?
Yes.
And sulfur didn't bring?
In the double bond formed, sulfur is not contributing any electrons. The electrons are only coming from oxygen. It is a dative bond.
Explained.
Is it okay now?
Yeah.
So let me explain to the students how this one is going to be approached, because I want to finish something remaining. Let me go to where we were. Now, this particular compound here, the first thing is to write the possible resonance structures. Now, the resonance structures, just like we did for the carbonate, do resonance. And once you do resonance structures, let me just continue. Then determine valence electrons. Then after determining the valence electrons, just a moment, I put on light here. So after that, you distribute electrons. Then determine the formal charge for each of them. For example, you can look at the resonance structures. Let me see whether I can load a resonance structure here for you. Just a moment. Let me see. You get something looking like, you see this? You able to see the structure that I've put there? So what is going to be happening here is the interchange of this particular oxygen here, because it can be here, it can be here. So you're going to have both three resonance structures. Now, once you have that, what is the total number of valency electrons? Now, this one has 6 valency electrons. This one has 6. This one has 6. This one has 7. And then you have an extra electron there. So the moment you actually distribute, you're going to come up with something like this. Then you can determine the formal charge. You see the formal charge, you realize that this oxygen and this oxygen are going to be the same. This oxygen is going to be alone. So you can calculate that. And once you calculate that, then you can see how they are going to be behaving. But here you're only going to see, because whether you are writing the single bond here or here, the formal charge that you're going to get actually is going to be the same in this particular case. Because after all, they are going to be resonance structures. You try that and then we can see. Something else that I want to say here is this. Remember, we are still handling last week's work, which I hope to finish today, so that on Wednesday we can begin the work for this particular week. I have checked, it's not a lot. But next week, I am told that we are supposed to be having the face-to-face practicals, which means we need to create time for the work that we are supposed to be doing next week. In fact, if you can arrange for a lesson in one of the evenings, I think up to around 9 o'clock, I think I would be okay with that. So kindly discuss and see whether you can provide an extra lesson for us to handle the remaining work. So allow me finish this, please. The bond length. The bond length here is simply the distance between the nuclei of 2 bonded atoms. And when we talk about the covalent radius, I explained that when I was talking about the bonding in hydrogen, the shortest distance between the nuclei of 2 bonded atoms, and you divide that one by 2. So that's why we are saying that the covalent radius of an atom is the value for that atom in a set of covalent radii assigned in such a way that the sum of the covalent radii of the atoms A and B predicts the approximate distance between A and B. That's the distance from the nuclei of the two atoms that are involved. The bond order is defined in terms of the Lewis formula, and this is actually what we call the number of pairs of electrons in a bond. And when you look at these specific molecules here, then we can talk about the bond length. We can compare the bond length. And what we know is that the more the number of bonds, then the shorter the bond. If it is a double bond, it's going to be shorter. If it is a triple bond, it's going to be even shorter. And that one is illustrated here. If you look at the Lewis structures or the Lewis formula of the three compounds that we have, we can say that the nitrogen bond should be shortest because this nitrogen bond here has a triple bond, while it is followed by the nitrogen double bond here. So these nitrogen single bonds are actually the longest. And we can give some values, for example, here. Look at the propylene molecule. Now, the propylene molecule is such that, let me pick up. The propylene molecule is such that there is a carbon-carbon here with a double bond, and there is a carbon-carbon here with a single bond. So if we were to compare these bond lengths, we would realize that this one is shorter. This one is shorter. This one is long. And some values are given down here. For example, the carbon-carbon here has 150 picometers. A picometer is 10 to the power minus 12. While this one here is 134 picometers. So the shorter bond is the double bond, and the longer bond is the single bond. In short, we are saying that the more the multiplicity of the bond shortens that particular bond. Now, then there's something we call bond enthalpy. This is the enthalpy change for breaking the bond in a molecule in the gas phase. We actually also call it the bond energy. How much energy is required? How much energy is required to break a bond? You require an energy equivalent to the energy or enthalpy of that particular bond. It is also a measure of the strength of that particular bond. The larger the bond enthalpy, the stronger the bond, and the higher the amount of energy you will require to break that particular bond. Now, from that, from the bond energies, from the bond enthalpies, we can actually determine what we call the enthalpy change for a process. And where does this one come from? This one comes from the fact that whenever a chemical reaction takes place, we do have reactants. Now, these reactants are of their atoms brought together by particular bonds. Those bonds have to be broken. Then we have the products formed. The products formed are formed by the atoms of the reactants after their bonds have been broken. So new bonds are formed. So there is bond breakage and the bond formation. Now, bond breakage is an endothermic process, while bond formation is an exothermic process. So the extent of those two actually determines the overall enthalpy of the process. And that is why we are saying that the enthalpy change is equal to the sum of the bond energies for the bond breakage minus the sum of the bond energies for the bonds formed. What I may actually say in a mathematical language is that delta, let me just write it in a text. but I won't write delta. So let me just use the pen. So delta H is equal to enthalpy of bond breakage plus enthalpy of bond formation. Why do we have, let me accept some student here. Why do we have this negative here? This negative is coming because this one is exothermic. It is exothermic. And being exothermic, it means that it is going to have a negative enthalpy. That's why if you have this one plus a minus, you eventually get what? A negative there. So you are just talking about the sum of the enthalpies in the process, in which case one enthalpy is going to be positive, the other enthalpy is going to be negative. That's why you have this negative here. So when the enthalpy is negative, then the heat is released, and when the enthalpy is positive, then the heat is absorbed. How does that interpret here? So when you have large bond breakage, let me instead write it. When you have large bond breakage and low bond formation, then what you are going to get is going to be such that the amount, is going to be such that the value that you get here is high, the value that you get here is low, and the answer is going to be positive, meaning that the overall process is endothermic. Now, on the other hand, if you get a low bond breakage and high bond formation, now, how is that one going to affect your enthalpy? The enthalpy is going to be affected so that this one here is going to be a low value. And what you have here for the bond formation is a high value. So when you have a larger value, a smaller value minus a bigger value, then the overall answer that you're going to get is going to be negative. And negative enthalpy will imply that the overall process is exothermic. And I think we have an illustration here. So estimate the enthalpy change for this particular reaction, and you are given the bond energies. Now, if you look at what we have here, we have a carbon-carbon double bond. A carbon-carbon double bond has got this amount of energy, because what we can say here is that we will have this bond broken. That bond is broken. So here we are. You also have carbon hydrogen bond broken. It is there. So if we can evaluate what is going to be happening here, you are going to have bond breakage. You are going to have bond breakage. Bond breakage is going to involve carbon double bonds. We also have carbon hydrogen, and we also have chlorine. Those are the three types of bonds that are going to be broken. And it is supposed to be such that if you look at the carbon double bond, it is only one. But the carbon hydrogen bond, they are four. Then you have carbon chlorine bond is only one. Again, when you look at what is happening here, you have new bonds that are formed. So you have a carbon-carbon bond, which is a single bond, and you have two carbon chlorine bonds that are formed here. Somebody would want to ask me, why are we not putting the carbon hydrogen bond in this formula?
Because both sides we have 4 carbon to hydrogen bonds, so it cancels out.
Brilliant. That's why we are not putting them, because they are going to cancel out.
Excellent.
Pardon? Somebody said something after the answer? So they are going to cancel out, and because they cancel out, we only concentrate on those head bonds. And therefore, we are going to have the amount of energy that is involved in bond breakage is 842 kilojoules, while the amount of energy released in the bond formation is 1,000 kilojoules. And when we subtract the two, then you are going to get negative 158 kilojoules as the net amount of energy that is going to be released to the surroundings in that process. So ladies and gentlemen, the long lecture has come to an end. There is a hand raised by Abdinor.
Yes, I have 2 questions to ask.
Yes.
The first one is, how can you determine, or what criteria can you use to determine the central atom?
There?
2, the central atom.
Yes.
The second question is this, where we talked about the delocalized bonding, and you said that it can change. Maybe, for example, if you have carbon that is bonded to 2 atoms,
Yes.
then it can change from maybe this atom to another atom. I was like asking, what if there are 2 different atoms which are bonded to carbon? Now, which of the 2 atoms will you choose? For example, the carbon is bonded to chlorine and oxygen. Where will you put the double bond between the carbon and chlorine, or carbon and oxygen? I've got those 2 questions.
Now the first question, how do you determine the central atom? This is going to be the atom with the lowest electronegativity. If you follow through, we are always taking the atom with the lowest electronegativity as the central atom in the polyatomic molecules.
Okay.
Now, the second question, please come again.
When we are talking about the delocalized bonding,
yes,
you talked about that the bonding can change maybe from one position to another position, right? Now, I was asking, what if the central atom is bonded to two different kind of atoms? Maybe let's say carbon is bonded to chlorine and oxygen. Now, when you want to put the double bond for the 2 different atoms, what criteria or what rule should you apply to say maybe it is going to be the double bond should be between carbon and oxygen, or maybe between chlorine and the carbon?
I think there's one example we had somewhere, which I want to go back to. There's one example I think we came across, and you go for the element with the higher electronegativity, is the one that forms a double bond. I think there's a place we had a carbon, 2 chlorines and an oxygen somewhere.
Yeah.
I'm trying to look for that, isn't it?
Yes.
I'm trying to locate. You remember that we chose to have.
Yeah.
It is this one here.
Yes.
You see here, we actually formed a double bond by using electrons from oxygen.
Yes.
And we didn't form using electrons from chlorine.
Yeah.
Number one, chlorine does not have a chemistry of double bond. It doesn't have double bond chemistry. But oxygen has. From general chemistry, chlorine does not have double bond chemistry, but oxygen has. Number two, if you go to what we call the electronegativities, you will realize that, let me check, I think I have the value somewhere. The electronegativity for oxygen is 3.44, while that of chlorine is 3.16. So here we have chosen the one with a higher electronegativity to be the one to donate electrons for the completion of a double bond.
Okay.
Yes, there was another hand.
Please, can I ask another question?
Yes.
When you are drawing the structure, like the one of sulfuric acid,
Yes.
can you go to that structure, please?
Let me go there.
Okay.
Yeah, this is where we are.
Yeah. We used the central atom as sulfur, right?
Yes.
Then why are we bonding the hydrogen to oxygen only and not to the sulfur?
Why are we doing what?
Why are we bonding the hydrogen atoms
Yes.
to oxygen and not to sulfur?
Now,
Are they
here, look, just look at the assumption we have just made. We began by making an assumption. Assume a skeleton structure in which the sulfur atom is surrounded by oxygen atoms. Is that assumption that we made?
Oh, okay, okay.
Yes.
So it's just an assumption. It's not.
Yeah, that is an opening assumption to guide. Eh?
Oh, okay.
Yes. Are you done with your questions?
Yes.
Okay, let us go to Nicholas.
Yes, Prof. Please, can you go back to that structure with oxygen, chlorine, and carbon? I don't know.
Okay. The one we had just discussed?
Yes, yes.
Okay.
I actually have a view on like the question that he asked. I don't know whether it's valid.
Let us go back there and listen to you. Yes, we are here.
Yes, so my view is that because let's say chlorine needs 1 electron to become stable, and oxygen needs 2 electrons. That's why oxygen will contribute 2 electrons and carbon also contribute 2. So that's the reason why the double bond is over there. And chlorine will contribute 1, and carbon also contributed 1. That's why the single bond is over there.
I think his question is, the question the gentleman was asking is, up to this point, the oxygen and the chlorine are already okay, in the sense that they have the 8 electrons. But carbon has 6, and we wanted to have 8. So the question he was asking was, when we are taking 2 electrons to form a dative bond, why are we taking them from oxygen and not from any of the chlorine atoms? That is how I understood this question. If I got it right.
Yeah, that's what I meant.
Yes, so now explain. Bring your explanation again, Nicholas.
Oh, like I thought he was asking why oxygen has 2 bonds and not chlorine. That's that's the reason why I was saying that, because oxygen needs 2 electrons to become stable. So the 2 electrons that oxygen is sharing with carbon, that makes the double bond over there. And chlorine is just an electron, yeah.
And I say that the oxygen was already stable up here.
Okay.
Yes. Yes, Anita? Thank you,
Yeah,
guys.
I have a question.
Yes.
On that very skeletal structure, where they are showing the lone pairs of electrons for oxygen.
Yes.
They are 6. Yet I'm seeing that oxygen has already contributed 1 electron for bonding to carbon. Like, I'm asking, why are the lone pairs still, like, why are the electrons outside still 6?
Okay. She's asking, why do we still have 6 electrons? That is something to look at. Now, how many electrons are there in oxygen?
Valence shell electrons, or?
The valence electrons.
There are 6.
They are 6.
Yeah.
So how is this bonding formed?
The bonding is formed by sharing of electrons.
So for example, here
I was thinking carbon is going to bring an electron. And also oxygen will bring an electron. They share. And they form this bond. So since oxygen has already brought an electron, so I think it should remain with 5. But 5, now I'm seeing 6.
Okay, let me follow through. Now, this is, one is coming from carbon, and the other one is coming from what? Chlorine, isn't it? Here,
yes.
One is coming from carbon, the other one is coming from chlorine. In this particular case, you know, carbon has 4, isn't it?
Yeah.
And it has, these 2 are coming from carbon. Okay?
Okay.
Please, I don't understand that part.
Not
Why?
understanding.
Yes.
Look, what are the valence electrons in carbon?
4, yeah.
They are 4, isn't
4.
it? So let me draw this. Let me draw carbon here. And then put an electron here, an electron here, an electron here, and an electron there. Are we together? Now, this chlorine here will come with an electron and a share, okay? So one of the carbon electrons has gone. That is where we have this bond. Is that okay?
That's very fine. And now we can see that chlorine has 7 valence shell electrons. It has taken 1 for bonding, and now it has only 6.
What?
Like, that is true because chlorine is only remaining with 6.
Yes.
So my complaint is on
Let me finish. I'm going slowly. Okay?
Okay.
The other chlorine here will come here. We have a chlorine there, isn't it? And that chlorine is okay. Up to there, are we together? For chlorines, are we together?
Yes.
So how many electrons has carbon used so far?
2 electrons.
No.
2.
It has used 2, okay?
Yes.
So how many are remaining?
Remaining 2.
Now, these 2 electrons remaining here are the ones forming this bond. Can you see this bond? Can you see this bond?
Yes, Prof.
That means the oxygen is coming to share these 2 electrons, but it still has its 6 electrons, these electrons here. At this point, oxygen has not shared anything.
That is kind of tricky because I'm still wondering why it should form a coordinate bond, because we say that a coordinate bond is formed when a bond is formed when electrons are shared by one electron. Like they
Yes.
come from one electron to
Yes.
form a bond.
Yes.
From one atom, sorry. So I'm still wondering why a coordinate bond, yet this oxygen has so many electrons.
Yes, look, eventually what will happen is this is the configuration that will be there. All right?
Okay.
This is what will eventually arrive at. In this configuration, we are going to have two electrons coming from carbon and 2 electrons coming from what? Oxygen. Now, this one is a skeletal structure. And in the skeletal structure, our purpose is only to ensure that this atom, and that atom have 8 electrons. And how can they have 8 electrons? At this particular point, we are not considering the carbon. We are not considering the carbon. So how are these 3 going to have 8 electrons? I'm sure you have no problem with the chlorine, isn't it?
Yeah.
But now, after the chlorines have formed their bonds, these 2 electrons are going to be available in carbon for bonding, isn't it? Already, oxygen has 6. It requires only 2. So in this particular case, it will only come and form dative. This is what we're calling the initial skeletal structure. At that particular point, you will realize that the 3 outer atoms have each an octet. Now, in this particular step here, a further rearrangement is going to occur. And what is going to occasion that rearrangement? The fact that the carbon atom here has less electrons than it requires. Yes, it has already given 2 electrons for dative bonding, but again, it requires 2. Therefore, 2 electrons are going to be given here for formation of a double bond, so that eventually carbon gives 2 and oxygen gives 2 for formation of this double bond here. What you have here is not the final structure. The final structure is this one here. I don't know whether that is clear now. Anita?
Yeah, I've understood it that in the first one, we are just aiming at obtaining an octet structure, but
For the outer
it's kind
atoms,
of,
for the outer atoms
yeah.
only. Okay?
Okay.
Yes.
Okay.
So can I end the lesson, students?
Yeah, it's okay.
So thank you very much. There are some requests you made in the morning, which I have not done. I will be consulting with my colleague so that we can do that. So have a very good evening. Please discuss and see whether you can give us an extra lecture even if it comes in the evening.
Okay.
So thank you very much.
Bye.
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 Bye, sir. Thank you.
Okay, bye.
I was chatting with her. She just sent me one message. I didn't reply.